We proposed Rip-NeRF, a Ripmap-Encoded Platonic solid representation to precisely and efficiently featurize 3D anisotropic areas, achieving high-fidelity anti-aliased renderings. The aliasing problem of NeRF is caused by its point sampling strategy. Though a pixel's color is the integration of all incoming radiance within the pixel's frustum, NeRF casts a single infinitesimally narrow ray per pixel, resulting in aliasing. To address this problem, previous works has used hash-encoding feature planes to accelerate queries, or region-integrated queries to avoid aliasing. Further, newer models such as Rip-NeRF combine these two implementations and their advantages. As we can see in the figure, the Rip-NeRF and Zip-NeRF respectively project the sampling sphere onto three multi-scale feature mipmap or spirally sample along the outer surface of the cone. However, these two solutions are either limited by isotropic pre-filtering strategy or significantly slowed down by multi-sampling. In traditional graphics context, Ripmap is a variant of mipmap, which is used to anisotropic pre-filter the texture, achieving better performance while maintaining relatively efficiency. To the end, we introduce Rip-NeRF, a Ripmap-Encoded Platonic solid representation to precisely and efficiently featurize 3D anisotropic areas, achieving high-fidelity anti-aliased renderings. We make three main modifications based on the Rip-NeRF. First, to characterize a conical frustum, instead of using isotropic ball, we use anisotropic ellipsoids. Then, to featurize the subvolume, instead of projecting it onto orthogonal triplane, we project it onto the unparalleled faces of icosahedron. Finally, to pre-filter the anisotropic area on a plane, we employ Ripmap instead of mipmap. We first state the reasons for choosing the anisotropic representation of conical frustum. As shown on the left, the isotropic area sampling used in Rip-NeRF cannot differentiate the anisotropic area from different cones, which leads to ambiguities in the representation. Inspired by Rip-NeRF, we characterize the conical frustum by an anisotropic 3D Gaussian. The two conical frustums are distinguishable under anisotropic area sampling. Next, let's see how the distribution of projection planes enhances the representation capabilities. As shown on the left, two 3D ellipsoids whose major axes are aligned along two different body diagonals of a cube share the same 2D axis-aligned bounding boxes on the orthogonal triplane, making them indistinguishable under the Ripmap encoding. However, their difference can be captured by an additional different-oriented plane. Based on this example, we empirically find that the more diverse the planes are oriented, the better their representation capability. In our experiments, we found that Platonic solid can take into account both simplicity and performance, while also provides a flexible trade-off between rendering quality and efficiency by selecting different Platonic solids with a certain number of faces. Last, anisotropic queries inspired by graphical pre-filtering further enhance the ability to inscribe anisotropy. As shown in left, the isotropic mipmap structure of Rip-NeRF makes its sampling area a square, which cannot precisely characterize the projected anisotropic 2D Gaussian, whose axis-aligned bounding box is essentially a rectangle. Inspired by Ripmap in conventional graphics, we propose Ripmap encoding to employ a Ripmap with learnable parameters to enable anisotropic area sampling in the neural rendering context, such that the anisotropic ellipsoidal footprint of a Gaussian can be characterized more precisely as shown in right. Finally, let's have a look at the qualitative comparison results.